Test, test.
Why don't we get going? Welcome, everybody. Yes, it's working. So it's my pleasure to introduce today's colloquium speaker. It's Professor Brice Menard from Johns Hopkins. He's a professor of physics and astronomy and also has appointments in departments of computer science and cognitive science. And if that wasn't enough, he's an external professor at Santa Fe Institute. So he got his PhD somehow both in France and Germany at Institut d'Astrophysique and Max Planck in Garching, after which he was a postdoc at the Institute for Advanced Study and a senior researcher at CETA, and then joined Johns Hopkins faculty in 2010. So he's a recipient of several different honors and awards, Sloan Fellowship, Packard Fellowship, and JHU President's Frontier Award. And something that I found interesting, he was selected as the 2012 Outstanding Young Scientist of Maryland. So this is working on topics on the interface of physics, astronomy, and machine learning and statistics, but also now in geosciences and biology. And I guess you'll be telling us something about that.
Thank you, George. Is the sound okay? Okay, great. Good. So it's a pleasure to be back here. I have spent the past couple of years looking more at neural networks than the sky. And so what I'm going to do today is to basically share the lessons that I have learned and report on some of the work we have been doing recently. Okay, so first, I would like to invite you to think about the different subfields of astronomy, and let's try to compare them in different ways. So this works. It doesn't. Okay, let's consider those three topics: supernova cosmology, large-scale structure cosmology, and studies of galactic dust. Okay, so if I ask you, which of these subfields are more similar? Okay. Typically, the answer is that supernova cosmology and large-scale structure cosmology are more similar. We tend to have this kind of scientists on the same floor of a given institute. The final goal is the same, to basically study the dynamics and geometry of the universe. But now if we ask the question, what kind of challenges do these people face on a daily basis, then the answer is very different. People who do supernova cosmology are very lucky. They have all the mathematical formalism apparatus they need to reach their goals. I'm not saying that what they do is not hard, it is, but they don't have any limitation of that kind. On the other hand, people who study large-scale structure of the universe or the spatial distribution of dust in the galaxy tend to be frustrated because they have data, but they cannot extract all the information they want to from this data. The reason is that they don't have the right mathematical language to do so. Okay? And in this sense, they share much more than people doing large-scale structures would share with people doing supernova cosmology. Okay? But the key here is to do point source photometry, and you can do all you need with Gaussian statistics, basically. Okay? This is not the case when you want to describe this rich morphological structure. Okay, so the key difference here is the complexity of the data. There is no generic definition of complexity, but I'm going to give you mine. Something appears complex when you do not have the adequate language to describe it. Okay. So let's look at an extreme case of this. If I ask you to describe this image, you don't even have to think. It's quite straightforward. Okay. Now, if I ask you to describe this image, you are going to struggle much more. This is not a lot of data. It's just 200 pixels by 200. It's only black and white. And we don't have to go very far to find this limitation that is due to complexity, due to the fact that we don't have the appropriate language to describe what we see. Okay, so you might say, okay, this image on the left is regular, deterministic. This one is more stochastic. Maybe that's why. That's a fair comment. But in this case, let's look at this intermediate case. This is also stochastic, but you will agree with me that you will be able to describe this, to describe a fair amount of this distribution. You can even ask the question, how many numbers do I need actually to say something about it? And in this case, it might be the density of segments, their lengths. And basically, that's about it, because the rest feels random. Okay, so you can say a lot about this. You are not limited by language, but on the right-hand side, the story is different. That's a very simple example, but this applies to basically all the scientific explorations we do in astronomy and beyond. So we have a spectrum with two ends, and in between we have a complexity frontier. If your work is on the left-hand side of this slide, you're lucky. You have the right mathematical language you need to describe this distribution. So Gaussian random field, an object with a lot of symmetries. This is an image of the sky with lots of galaxies. As you know, we can turn this into a catalog of sources. The simple fact, the ability of going from pixels to a list of objects already shows that we have a good language to describe what we see. And these objects, in order to extract information, what we are going to do is to just take moments of the light distribution. The zeroth order moment is the flux of the source. The first order moment is the position. The second order moment is going to be the size and the ellipticity. And so just using this polynomial moment-based approach, we can extract a lot of information from this image, and we can basically proceed with the next steps. On the other hand, if we have to deal with these images, I don't know any way of turning these structures into catalogs of objects. The definition of object is already problematic in this case. And when studying them, the frustration is that usually we don't have the right mathematical language to extract all the information we want to extract from the data. All right. So here, the key is complexity. We find complexity in many forms. We find it in the signal we want to study, images, spectroscopy, time series, and text, for example. But for some people, the complexity challenge is not in the object of study, but what's in the way. It can be in the noise or the calibration that is involved. For example, people who want to do imaging of exoplanets. Okay, so the exoplanet is just a point source there. It's a relatively simple object, but it is embedded in a very complex sea of fluctuations due to the tails of the point spread function of the central star. And in this case, this is the complex object that is in the way, and that's a source of noise. Okay. For others, complexity can be in nonlinear responses, intra-pixel variations, and in some cases, it can also be conceptual. Okay, you might have to manipulate high-dimensional structures, non-Gaussian, complicated likelihoods, etc. Okay, so it can be there in many forms, and we have to deal with it. So what happens when data is complex? As I said before, the challenge is not the amount of data. I gave you a couple of examples already. That was not a lot of data, and complexity can already be a limitation. When it's there, the limitation is not about signal to noise, and it's not about systematics. Yeah, I'm going to repeat myself a little bit here, but so the challenge is the ability to extract information from data, and that's a question about language, okay? Mathematical language, or which language in general are we going to use to extract that information? So as you know, around 2012, everything changed. So the generic solution is now available for all these challenges. And as you know, the answer is, let's use neural networks. Okay, we've seen many applications of neural networks in astronomy and beyond. We know they work really well. But the key question, and that's what I'm going to talk about today, the question is why? Why do they work so well? What do they learn? And how do they learn? Okay. We would love to have answers to these questions, because then we know how to better use them, how to better select questions to address with this technology. Okay, so now I'm going to tell you some of the lessons I have learned working in this field. So first, the key property of neural networks is that they enable what is called geometric stability. And they can do that with different symmetries. So what do I mean by this? What is geometric stability? The idea here is that if we have an estimator that has input-output, a function, a mapping, often we desire that if there is a small perturbation in the input, I want the output to have a small perturbation as well and not to blow up. Okay, so this is this geometric stability. It's a very desirable property of estimators. And the advantage of the neural network architecture is that they can enable that in many forms. So we have to deal with data from different domains. We can have data on a grid. And that's typically what we have in astronomy, images, spectra, time series. We can have continuous data. We can have data on the graph, data on the manifold. There are different domains on which we get data. And these domains come with different types of symmetries. Okay, very simple one that we have to deal with a lot is translation symmetry. Okay, we can have rotation, permutation, isometry. Now, for each of these domain and possible symmetry, we can actually have a declination of the neural network architecture that's going to basically implement this geometric stability given some symmetries. And here what you can see is the zoo of many of the network architectures that are out there. You've heard of convolutional neural networks, graph neural networks, transformers that are used for language models. They are all different declinations of the same principle. This geometric stability, I want small perturbations in the input to lead to small perturbations in the output, or no perturbation at all, in different contexts with different domains and symmetries. Okay, so that's really one of the keys that's behind all of that. All right. What was the situation before we had neural networks? Okay, and I think it's instructive here to step back and look at the history of physics and astrophysics and try to understand how we've been doing things for a long time. As physicists, we've been using the empirical cycle for centuries. We have the world out there, observations of the world. The ultimate goal is to extract a fundamental principle that describes many of the phenomena out there. Usually, this is not done in one shot. There's an intermediate step which requires noticing the regularities in the world, in the data, the patterns that are out there. And so from these patterns, with some significant intellectual efforts, sometimes we can extract a fundamental principle. Okay. Now, how have we been doing this for centuries? We've been doing this using one very specific language, one specific mathematical language, and that's the language of polynomials. Okay. This has been extremely successful. The equations of physics are written in a polynomial language. If you take gravity, Maxwell's equations, Navier-Stokes, we do only two things. We change the power of some variables, and we take derivatives. Derivatives in real space are polynomials in Fourier space. So we are basically using this polynomial language, and it has been extremely successful. That's how the equations of physics are written. And often, we basically use the same language to describe the patterns that are generated by these equations. That does not always work very well. Okay, let's take the example of gravity. Okay, we know that this very simple principle, if you take lots of particles with this force, lead to these very rich patterns out there. And what happens is that we have the tendency to describe these patterns, which are solutions of these equations, using the same language. One motivation sometimes comes from perturbation theory, which invites us to use Taylor expansion. So again, the polynomial description of variations in data. In this context, what we are going to do is to use basically a power spectrum. That's what people have been doing in cosmology for many years. But if we do this, what happens? We are basically the power spectrum. Okay, it's a polynomial description of a field. It's a second order polynomial with maximum entropy. That's this approximation of a field. If we extract the power spectrum from this image, and from that power spectrum, in the maximum entropy distribution context, we want to regenerate new realizations. This is what we get. Okay, so these two images have the same power spectrum. What we have on the right, we have only used the power spectrum, so we end up with a Gaussian random field, and that gives us an idea of the type of information we have extracted from this image, and obviously, it's very partial. Okay, there's still a lot to extract that has not been extracted using that second order expansion. So there's a bit of a mismatch between the language that's extremely powerful and successful at this level that does things only partially when we are in the world of patterns. So This is what we've been doing. That's my claim, at least, for centuries. And this comes with limitations. Okay, I showed you one example of the power spectrum. And now, what we have learned from neural networks is that there is another type of expansion that we could use. And this is it. This is what neural networks do. It's a cascade for some input X. It's a cascade of matrix multiplication or tensor, nonlinearity, which is applied pointwise. And we're going to repeat this, matrix multiplication, nonlinearity, etc. This is another type of expansion, okay, that we realized the power of this expansion only recently, I would say. And it can do great things for us. Okay, so what now we know that this is basically the mathematical expression of this, of one possible neural network that does some mapping between input and output. Okay? What happens here is that often in this expansion, we are actually expanding the dimensionality of the signal. And so at the end, we want to shrink this to the desired dimensionality. So we have a linear projection at the end. Okay? This is what it does. All right. You have all heard about neural networks. And in the scientific context, we often hear about some limitations that come with them, that a lot of training data is needed in order to use them, and that they are black boxes. And what I would like to do during the rest of the talk is to show you that this is actually not completely true. Okay, and I will show you counterexamples in each case. All right. So let's try to understand what neural networks do. And in order to do so, I'm going to start with something that you all know here, the power spectrum. Okay, this is a very classical tool in astrophysics and cosmology. So let's look at it. You are used to think and manipulate the power spectrum in Fourier space. And I'm going to do things very simply here. I'm going to use the power spectrum in real space. Okay, so if I have, let's say, an image I want to extract the power at some frequency K, I can write my power spectrum in real space as this operation. I convolve my image by cosine and sine function. I take the square modulus, and then I average over all the pixels. All right. And I guess you have all used this in your work so far. What you have not realized is that this is actually a neural network. Okay. Perhaps it's not a good neural network, but it can be thought as a one-layer neural network. And let's have a look. What I'm going to do is to re-express this using the formalism of neural networks. If you remember what I showed before, is that neural networks, they cascade these matrix multiplications, nonlinearities. Here, I'm only going to do it once, and then I have my linear projection at the end. Okay, so I have two different views of the same object here. And then I can identify all the terms here. So in this case, the matrix multiplication is going to perform this convolution by the sine and cosine. My nonlinearity is the square modulus, and then I can average over all my pixels. Okay. Now, from this point of view, let's try to basically question, or let's try to see the pros and cons of each of these different components. And I'm going to do that for you visually. So let's take an image. This is my initial image. And let's try to compute the power spectrum of this image using that path. The first thing I need to do is to convolve that image with my sine and cosine basis. And when I do this, I get basically two images. There is the modulus, and there are the phases, or the real part and the imaginary part. Okay. And I would like you to notice here that what I have done is dimensionality expansion. I started with one image, now I have two images. Okay. As you know, the power spectrum is only sensitive to the modulus and not the phases. So we are going to focus on the modulus here. And I would like you to realize that by doing this convolution, I create a new image. This is called I1 here. Because the convolution is done with a completely delocalized kernel, my sine and cosine functions are going to infinity. So they are basically washing out all spatial information that I have in the image. Okay, and that's why this I1 image is just a constant. Okay, and I'm going to do something strange now. I'm going from that image, which is a constant, I'm going to pull one number and just take the average for that image. I know it sounds a little bit weird because it's just one number, but that's what I do. And that's how I extract the power at a given frequency in my image. I have my P of K at that K. All right. So now we can ask, what could we do differently here? Okay. One limitation we have is that we have used this delocalized kernel, the sine and cosine, that washes out all spatial information. It's good because that's how we get translation invariance, but we get translation invariance at the cost of washing out this information. Instead, I can use a localized kernel. Okay. This could be, for example, a wavelet where if I do a convolution by this kernel instead, I get now this modulus and this phase images. Okay. I can do the same. So I have one image I1, which is now defined differently as the one at the top. And I can pull one number from it, one coefficient, by just taking the average of the image. So here, I now have two different coefficients, two summary statistics. Okay, the one at the top tells me about the power at that frequency. This does not have the unit of a power. It's a different type of summary statistic, but it is informative. And it tells me something useful about the content of this image. Okay. Now, as you know, we do this kind of operations through the dimensionality reduction. And so in this case, we are getting rid of the phases. We can get rid of the phases both for the power spectrum and for this new path that we have taken. By doing so, when I remove the phases, when I discard the phases at the top, this is information about the translation of the entire image. But now the phases here, they are information about translations on very small scales, so on scales that are smaller than the kernel that I have used. And usually we don't really care about this kind of information. So we are happy to discard. Okay. So the main difference here is that, I have changed my kernel from completely delocalized to localized. But now there's a very interesting advantage by doing so. What I can do, I can repeat the operation. I can only do this meaningfully at the bottom because at the top I have only one number. There's not much I can do with one number. I've got that number already. But at the bottom, I can repeat with new wavelet, a new scale. I get a new image. Okay. And I can do the same. I can pull one number from that image by just taking the average over the image. So what I have now, I have two summary statistics that tell me about my distribution. The advantage is that these summary statistics, in both cases, this is first order, this is second order, but in both cases, they are first order in the data. I have not raised the power of the input. And that's key if you want to have an estimator that has low variance. Okay. So this is a different way to extract information from signals. I have done that just focusing on one scale. I can do that now in a multi-scale approach. Okay, so I'm doing it with three different scales here. At the top, that's how I would extract P of K, my power spectrum as a function of frequency. At the bottom, I can do this as well using this different formalism. And I can now cascade this because I know this is not the end. It is the end of the power spectrum, but it is not the end here. I can start to cascade this. I can repeat it once. And as you can probably imagine already, I can repeat that many times by cascading more and more convolutions, nonlinearities here. And here you might recognize the mathematical formalism of these neural networks. Okay, so this is an estimator that was introduced by mathematicians. It's called the scattering transform. It's more than 10 years ago now. And it's only recently that it's made it to astronomy. So let's come back to our power spectrum. We've seen that we can think of it as a neural network. And if we want this estimator to be a better neural network, we have to do two changes. We don't want to use a delocalized kernel. We want a localized one. We want to do a convolution, for example, by wavelets, but it can be by any function we like. And when we apply the nonlinearity, we do not want to raise the power. There is no reason to do that. We can use a modulus, an absolute value, a ReLU, or other functions in such a way that our estimator will always be first order in the input. Okay, and that's how you guarantee stability, convergence, low variance. Okay, and those are properties that higher order statistics, for example, don't have. All right, so if we do so, we have great benefits. We have an estimator that is quasi-insensitive to small perturbations. We are quasi-translation invariant. we can cascade or iterate this operator many times to extract more and more information from our data. And as I said, we keep an estimator that is always a first order statistic. Okay, and that's a great property to have, and that's how neural networks operate. Okay, and that guarantees stability and low variance. If you want to learn more about it, this was probably a bit too fast to grasp everything from it. With my former grad student, Sihao Cheng, we wrote a guide to the scattering transform, which is online. The original papers were written by mathematicians for mathematicians, not necessarily an easy read, but this is written for physicists. So if you want to know more about it, here's a reference. And now I'm going to show you work that I did a couple of years ago with Sihao. All right, so now let's use this estimator and let's see what it can do, and you're going to be impressed. Here are 5 different fields that we encounter in physics. What I can do is use this estimator, and I'm only going to use a second order expansion. Okay, so I'm going to extract these coefficients in the way I present it, only up to second order. So I pick a number of scales, and at order 1, I extract the coefficients, and at order 2, I extract the coefficients on those scales. What I get then is a set of summary statistics. It's rather compact. You know, in this case, I think we've done that with something like 20 to 30 parameters. And from this set of coefficients, I can regenerate new fields. Okay. If I was doing this only with a power spectrum, I would only get these Gaussian random fields. But this is much richer than that. And if just from these coefficients, I regenerate new realizations of these fields, this is what I get. Okay. So from this very compact representation, I have the ability to describe very rich morphological patterns, and not in a way that is just specific to a given field, but this is, you know, generically over many types of distributions. Okay, so this is extremely powerful and rather simple. This is done without any training. Okay, you can think of this as a 2-layer network that is fully deterministic and can be directly applied on one image and extract its summary statistics. Okay. All right, we can use it for all sorts of interesting applications. I'm going to show you one exploration here in the context of oceanography. Some colleagues of mine told me about this interesting data set. This is, you know, satellite remote sensing measuring sea surface temperature. This data, and it has the full coverage of the Earth, comes with tiles, which have a size of about 100 kilometers on the side. So we have about 100,000 such tiles. And people in oceanography were struggling trying to organize all these tiles using neural networks that were trained on the data. And so what the problem lines of each tile. I can use this coefficient very simply to organize the data. And what I'm doing in what you can do, for example, yeah. Okay. If you visualize the neighbor, very straightforward. In this game. Another example is we have millions of galaxies made to start this and for tonight, just object that into the dimension again. Very straightforward. No training, no neural network. I can organize the data of that. Good. Navigation technology. Performance compared to the protein. So this which starts with the different. What I'm showing you here is that this is the company power, company power on the mega pattern. Because on it, it's going to I do the same type of analysis in capturing coefficients. Okay, this is on par with the performance of convolutional learning. This shows you that it really need to use these networks to train them on their function. What is important to point out here is the number of coefficients given to manipulate not affecting the you want more control on the all right. So yeah, 100 simulations has now been applied to bigger data. Around the data release, see how China has done the full analysis from different all the way to the not in certain that way we can fact. So we go for different information, we can look beyond without information. Okay. So what I have convinced you that without training on lots of data, first by using this kind of output, you can do it. What is other than that? Very complete, while for many applications, now you want to how they have the last law, more than 5 now the level of complexity is much so what we have the problem because so I cannot do that the way it is very deep. If I want a deeper expansion, I want to go beyond it. That's the only. So when you only use the first part of the result, now we are predicting what happens to another simplification I can use Okay, now let's try to compare neural networks. The two neural networks, they have different random initializations. Each time, the random initialization all the way to the Now I would like to know, when I train this network to perform a task and some data, the question is, can they learn the same thing or not? Okay, if people have looked at this on a number of years, what I can do, I can look at the first thing, I can compare the weight of these two networks and see if they are similar. It doesn't make sense to compare the neurons individually, they are not. But what we can do, we can look at this statistically. I can look at the eigenvectors of the weight covariance. When I do that, and I compare the eigenvectors, the same and people have known that for a long time, and then actually visualizations of the weight of the first layer of networks in more than 10 years. Okay. Yeah, I'm going to if I repeat, let's make this. I think what I do. No correlation at all with the magnetic charge of one lost. This is the origin of the planet. But later one, some of that doesn't make sense to compare neurons individually in this large network. But if we look at the statistics at this way, then we can meaningfully compare them. But they are two. That's a good problem that is behind this neuron. So why is that? That's not a problem. What I'm showing you here, actually, I got the different level. Therefore, they are using the same problem. Now, the first area can be found visualization. That visualization is basically going to get down rotation. The way things are going to express that value. So that's one area then each neuron individually we expect one axis of the rating effect of the length. Therefore, economic initialization is going to happen. We have this random basis that fortunately, what can this collaborators in Paris? Led by Laurent Angus, who was the greatest student there. We managed to find a way to basically counteract these random rotations and to realign networks in the common. So again, the random basis Okay, this one of it. But there is a way to estimate this random rotation that is done by which we are and basically we do it. We can actually meaningfully compare neural net. So for now, if I do this alignment procedure, and I go back to layer 2 of this network, I can now meaningfully compare the eigenvectors of the vectors. But I see that at any network, or have they learned locally? What we can do and okay, and want to and see where the performance comes from. What I can do is here that it will over parameterized, and that's true, that's true. But at the end of the day, you can okay, so now we can ask interesting questions. Now we have this tool to meaningfully look and compare, to look at neural networks that they have linear encodings and compare pairs of them. So what I'm going to show you now is in the context of ImageNet. That's one of the classic datasets. And actually, when we research, it has about 1 million images and 1,000 categories, so 1,000 classes. So what I can do is pair of networks, train different conditions and compare what they have learned. So now I'm not going to show you just one layer. I'm going to show you a full network, 7-layer network. So we have conditions here. First thing I want to do is to use this alignment procedure. Otherwise, I will not see any correlation at all because of this random basis. But once this is under control, I can compare different things. So here, I have two networks trained on ImageNet with different random units. What I'm showing you here, we'll continue and do another type of experiment that will change the width of the network, the number of neurons per layer. I'm changing the architecture. I find this network on the data set again. I found that. Yes, now I'm going to do another test, which is even more remarkable. Now I'm going to select different categories in the data. So the data has 1,000 categories of classes. I'm going to select the first set of 100, randomly chosen, and another set of 100. Okay, so now we have those networks are looking at different data. If I compare what they've learned, I find that they've learned the same thing. So, to summarize this, what we are learning is that around most of the layers, all the layers except the last one, come back to that. What we learned is that those networks are created encodings that do not depend on random units after this alignment procedure. That do not depend on the width of the network, which is the number of neurons per layer. Does not depend on the stochasticity of stochastic gradient descent, which is the algorithm that is used to find the neurons and perform that. It does not even depend on the training data sets from the network. Okay? What this means is that if I stay in the context of natural images, I can take any classes of natural images and what it learns the grades that are shared between the images. What this is showing is that there is universality in learning. That these neural networks seem to be complicated and very stochastic, but they are much closer to deterministic function. they will learn encodings that do not depend on any of the parameters and do not depend on which dataset exactly we use in the context of natural imaging. As long as you stay in this universality class of natural imaging, any dataset will basically be the similar. So the story is much simpler than what you think or what you feels. Yes. Okay, so if you do not, if you apply these notations on untrained network, for example, you don't see any of this those will all be zero. So you can do like a null test if you want, and these correlations will not exist. So we do know that those are the features learned by the networks, and they are not, this is not produced by the line solution. We can also look at the spectra, those are eigenvectors for variance matrices. We can also look at the spectra, and there is plenty of information there that also shows the learned subspace, something like that. But we can also see this evolving as a function of training time. I can show you again. Yeah. So this is what, for example, the second row shows. We are changing the width. So one network here is 10 times bigger than the other in terms of number of neurons per layer. So this is insensitive to the width of the network. And again, this is because the subspace of what is being learned is much, much smaller than the number of neurons. Okay, so as soon as you have enough capacity, then you can increase the size of the width of the network. It has no effect. Okay. All right. So there is this fantastic property, there is universality in learning. Okay, so all these networks basically end up to converge towards the same encoding, even though you use different types of data in a given context. Okay, this is in the context of natural language. But presumably to do that in astrophysics, you learn from observer of this type from one telescope or another telescope. You will basically have networks that will learn similar features. This also explains what is called transfer learning. Okay, people did notice some years ago that we can train a network to perform a task. Then we can just retrain the last few layers on a different task and let it be. Okay, that's much better. You don't have to retrain for the task. This is the explanation. This is the origin of the transfer learning phenomenon. The two points is that and finally we can data sets. The same visual vocabulary that we make this stuff if you stay in the same universality classic. Yeah, this is showing you in the class theorem that the solution exists. But it doesn't tell you anything with the part you get there and what it looks like. Right, so now you exactly. Okay, let's be careful here. The class is not the same. When you look at different sets of the class, okay, so the different class is different. Even though it's different, for 6 out of 7 layers, we learn the same thing. It's a little bit. Okay, now we can ask questions. So, for example, question for you: which classification task is more difficult? Okay, so cats and dogs is more difficult. We can do that. We have much more in common. So then find set of features that we think it's much harder. But now I ask you 20 times. How much harder is it? How many features do I need to learn to distinguish cats and dogs versus cats and dogs? Now I have the tools to address this and to give you an answer to that question. What I'm going to do is to do that even more generically. To go back to this table. Remember, 1,000 technical and 2 technical they are instructions, okay, so these are 3 they are equated with 13 different levels. Okay, so when you look at the bottom of this branching, you find that there is a and that I can be identified by animations. So what I can do here is what we have done is we've taken the deepest branch of the tree and we will hold that down. We are going to inspect all the things around that branch. And this is what because it's natural states. Well, okay, at the top, I can see that for the two bits of the dimension of 85, and for the one that is 2 years, if I sum it over all the layers. And so, the factor 2, difference between the others classification times and projects. Now, I just want to show you that this is not a black box. You can actually do the blocks. You can see, look at the encoded in the structure. In many ways, you don't know how to recognize of the community. But this one with the dimension of the here, that the structure it has a shape and slowly we get back to the that is done by the team. Yeah. See the simple example of the pairs of classes. I can now show you what happens if you have more demanding time. This is how many features the networks are running with 10 classes, 50 classes, 100 classes. Okay, so they have to run more and more. One. But what you see is higher feature resolution. And at some point, this starts to replicate. Okay, I went to 1,000 classes. So what is so what's happening here is that as we increase the number of classes, the resolution with which we want to find the space of variables. Some point, that nobody else defines the number of classes. We want to make the number of classes we can have the result of and because the longer depends on this is the region of the foundation model. We learn a lot of data, we talk a lot of classes, the one that is no longer really matters, that will depend on the classes. Even outside, only the universal. And that's what this foundation model is going after. But that's one from their and so one is hasn't got like rich, and there is no need to increase the number of plastic data. We have new legs of the big found to be other companies of that. What when they will find to specific things. All right. So I hope I have convinced you. Instead of doing our only So maybe the problem we have in physics. And I hope I have to convince you that only not only they are not like that. You can find black dots. We know how to look at it from the right point of view, introduce it to 9 procedure. Actually, with a lot of clarity. We can look at the eigenvector feature in them. And to me, one of the most interesting results that you can see that there is universality in the networks that are learning from different data sets, context, network will learn the same feature that will not very much determine which data set they are using. So it depends on much more deterministic. All right. In the last minute or so, we have to now take these ideas and use them in the context of neuroscience and biological. I've shown you how to compare artificial networks. Now what we are going to do is work done in question. So the data set that we have to do is kind of experiment. Some people have been using fMRI scanners. They have seen lots of that information. And so what happens is that for each neurons that we can now as I showed you. If you want to compare neural networks, we have to do this rotation. Probably the same for the brain. My synaptic connections are not the same. The same alignment because expectations and alignment in those places. Actually, compare the picture to have beyond that. What we find in context. Comparing two subjects, we have an alpha data set statistics on the minimal sector. Now, very similar to biology. In brains that we have okay, so that's it for the quality in learning. But we learned since we converge about one structure, we met we have fundamental structure of brains, relatively mathematics. But what is interesting is that this structure relatively similar. So we can see the visual world and no way around this. This is done procedure. So very simple. All right, I'm going to summarize this entire story. I'm going to do a very simple summary. I hope I have convinced you that you are happening in the past. Basically, the realization that there is another way to expansion from just like variations in data. Instead of using this polynomial approach, a new type of expansion. And they extract a lot of which from which without any just using that multiplex data and learn. And what I want to refer you today is that this learning process is not as obscure as it might seem. We know how to look at the workings of neural networks. The key is to use this line of then you find a lot of structure. We can look at its dimensionality, we can look at its state, its statistical properties, and we can say a lot about the encodings that emerge in the neural network. So we start with apparent problems of neural networks and they need a lot of training data and they are black boxes. Hope that by now that one is not the thing. You can actually use the technology to offer very limited data, even one image, one specific. You can do that. And if you need to do more than the expansion, then it's another black box. So according to this box, we think that things like has a lot. And so moving forward, I think what happens that instead of having us use our brain to look at data, what we can do is to have neural networks look at data, extract these rich patterns, and hopefully we can now use our brains to look at inner workings of neural networks and be one step closer to go from patterns to the foundation principles. Thank you. Neural networks will be complete. In this case, trained with same data on the same task. So you have two views of the same object. And so what you can do, you can do something that is which is in a two space of different dimensions. The goal is to basically find the rotation of one space that correlates with it. You can do that with different dimensions. Yes, at the end, basically, object space of the and one is bigger than the other. And we are going to take the section of the and we're to find that in the section of the
Question three. Thank you, speaker again. And just to remind you, there are a couple more open slots to talk with him tomorrow morning if you're interested.